today we will continue to talk about data structures. So last time we talked about trees, and today we will first give a very quick review of the tree. So here is some key information about the tree, which include roots, parents, children, and subtree and leaf nodes. Okay. So today we will be specific on a type of a tree. And last time we talked about binary trees. So this is a kind of algorithm, or you can say a very specific kind of tree that is called the binary search tree. So this kind of tree is a special type of binary tree in which the left child of the node has a value less than the node's value, and the right child has a value greater than the node's value. So this property is called the BST property, and it makes it possible to efficiently insert and delete elements in the tree. So the root of a BST is the node that has the smallest value in the left subtree and the largest value in the right subtree. So each left subtree is a BST with nodes that have smaller values than the root, and each right subtree is a BST with nodes that have larger values than the root. Okay, so you can look at the graph here. So this is a typical kind of BST. So you can see that, for example, the node 3 is less than its parent 8, and the right child 10, for example, is greater than its parent 8. Okay. So binary search tree is a node-based binary tree data structure that has the following properties. So first, the left subtree of a node contains only nodes with keys lesser than the node's key, and the right subtree of a node contains only nodes with keys greater than the node's key. So, for example, if you consider the node here, and you can know that the children of this node is, for example, 14 is always greater than 10. So this is the kind of property of this tree. And this means everything to the left of the root is less than the value of the root, and everything to the right of the root is greater than the value of the root. So due to this performing, the binary search tree is very easy. So the left and right subtree each must also be a binary search tree. And there must be no duplicate nodes. BST may have duplicate values with different handling approaches. So here is the handling approach for duplicate values in the binary search tree. So you cannot allow the duplicate values at all. You must follow a consistent process throughout. That is, either store duplicate value at the left or store the duplicate value at the right of the root, but be consistent with your approach. So we can keep the counter with node, and if we found the duplicate value, then we can increment the counter. So now we'll talk about searching in a kind of binary search tree. So searching in BSD involves the comparison of the key values. If the key value is equal to root key, then search is successful. If lesser than root key, then search the key in the left subtree. And if the key is greater than root key, then search the key in the right subtree. So here is the BST searching algorithm. So first we check if the tree is null. If the tree is not null, then follow the following steps. First, you have to compare the key to be searched with the root of the BST. So if the key is lesser than root, then you will search in the left subtree, because you know that all the nodes in the left subtree is lesser than the root. So if the key is greater than the root, then search in the right subtree. If the key is equal to the root, then return and print search successful. So I can show you some codes for searching a BSD. So here is a class which implements a BST, and you can first look at the method to insert a node into the BST. So you can see here that if the key is less than the node, then you will insert it on the left of it, and if it is greater than the node, the current node, which is the parent, so you will insert it and let it be the right children of this node. So you can reverse this kind of process when you search. That is, if the current node, if the key you want is greater than the current node, then you will go to the right children, and if the current key is less than the current parents, then you will go to its left children. Okay, so now we are talking about tree. So first, heap. It is a special tree-based data structure in which the tree is a complete binary tree. So here are some operations of a heap data structure. First is called heapify. So it is a process of creating a heap from an array. The second one is insertion. It is a process to insert an element in the existing heap on complexity of log n. And the third one is called deletion. So it is deleting the top element of the heap, or the highest priority element, and then organizing the heap and returning the element with time complexity of log n. And the last one is called P. It is to check or find the first, or can say the top element of the heap. So generally there are two kinds of heaps. So the first is called max heap. So in a max heap, the key present at the root node must be greatest amount of keys present at all of its children. So the same property must be recursively true for all subtrees in that binary tree. And the second one is called min heap. So in a min heap, the key present at the root node must be minimum among the keys present in all of its children. The same property must be recursively true for all subtrees in the binary tree. Okay, so so now I'll talk about how to remove the largest item from a heap. So for example, we can have a max top heap here. So we can look at this one. And then we know that it is a max heap because we know that this one is largest and these are smaller than this node. And you can see that in this subtree, it is also a max heap because this one is larger than its children. So what if we want to remove the largest item, which is the root of the heap, and while keeping its structure to be still a heap? So first, we make a copy of the largest item. So for example, we can have a variable outside this data structure and store the key of this node. Then we remove the last item in the heap. No. So we will replace this root with the smallest item in the heap. So that is 5. So you will get a heap, or not a heap, a binary tree in this type. Okay. So when you do this, it is still not a heap because 5 is the smaller node inside this binary tree. So you need to still transform it, or we can say to heapify it to a max heap. So we will use a process called sift down. So we shift on this node, that is 5, and we first compare its two children, that is 20 and 12. So we find that 20 is the greatest one. So we'll exchange their locations. So you can see that 20 now becomes the root of this binary tree, and 5 will go downwards to here. And we can know that 20 must be the top node for this kind of heap, because the original heap is structured like this, so it's 28, 20, and 12. And because 28 is removed, and its two children, which are the largest nodes for their subtrees, are 20 and 12, and the larger one in 20 and 12 must be the new largest node inside this new tree. So it can be the root of this tree. And then you will continue to do this process of shifting down the 5, and then you will get a max heap. And then you can return the largest item you want. That is 28. You have already stored that in another variable. Okay. So now we will talk about inserting an item in a heap. So, for example, we have a max heap here, and then we want to insert a node with key value, for example, 35. And then we first put it in place. Because this heap is a binary tree, so it must be put in this place. And then we will shift 35 up. So we compare 12 and 35 first, and we find that 35 is greater than 12. So we will exchange their locations. Yeah. Now 35 is placed in this location, and you have 12 to be the leaf node of this binary tree. And then you will continue to compare 35 with its root, with its parent. So you will find that 35 is still greater than 20. So you will exchange their locations again. And now 35 will be the top of this heap, and 20 will be its child, and now the max heap is completed. So, for example, if we don't have a 35 here, and if, for example, if we have a if we want to insert a node with key value 18, for example, then after shifting it up once, that is, you have 18 here and you have 12 here, then you find that 18 is less than 20, so you will just pause and you already get a complete max heap. Okay. I think that's all for today's activity, and we'll talk about maybe continue to talk about other details of heap in our next activity, and good luck for your exams. Thank you.